welcome to Organic One Lab, and today we will be performing thin layer chromatography for the analysis of analgesic drugs, or TLC for short. First, we're going to talk about chromatography and what it is used for. Chromatography is an analytical technique commonly used for separation of a mixture of chemical substances into its individual components. Components can be separated by different properties such as their polarity, their different sizes, their different charges, and among many other things. Why do we need it? Because it is a very handy tool for purification of mixtures and is often used for substance identification or even reaction monitoring, which are common techniques used in organic chemistry. The chromatography technique we will be using today is called thin layer chromatography, or TLC for short. TLC is a method of separation by polarity. Using a commercially available TLC slide, which is shown on the image below, right there, a mixture is going to be spotted on that TLC slide, which is shown right there. A mobile phase will be selected and will be allowed to run up the slide, which will separate the mixture based on polarity. Next, we're going to discuss some helpful terms that will help you understand the lab a little bit better. First, I want to discuss the mobile phase. The mobile phase is a solvent that is allowed to work its way up the TLC slide once it is placed in the TLC chamber. The mobile phase can vary in polarity depending on the analyte. Next, there's the stationary phase. The stationary phase is the substance that doesn't move. In our case, it's going to be silica gel. More specifically, it's going to be silica gel coated on a rectangular slide that will be provided for you. This is shown on the image below. Then there is the solvent front. The solvent front is the length which the solvent travels, which is shown right here. The solvent front is often marked with a pencil, and you will see why later on in the presentation. Then there is the origin, which is located right there. The origin is where the sample is going to be spotted. And lastly, I want to discuss polarity. Polarity should have been discussed in depth in Gen Chem, but we are going to review it a little bit just so you can understand the concept a little bit better. A general definition for polarity is that in chemistry, polarity is a separation of electric charge leading to a molecule or its chemical groups having an electric dipole moment. Let's take water for example. Water is an example of a polar molecule. It has a polar covalent bond, and what that essentially means is that electrons are not evenly distributed in that bond. Oxygen, being the more electronegative atom, is going to be carrying a more bulk of the electrons than the hydrogen area. This is indicated by the partial negative and the partial positive, which indicate a dipole moment. Another way to think about it is that the electrons are going to be more localized in this oxygen area versus this hydrogen area because of oxygen's higher electronegativity. Another way to think about it is that polarity is more of a spectrum. Let's take water and methanol, for example. They're both polar molecules, except water is more polar than methanol. That's because water has more localized electrons in a single area versus methanol, which is more evenly distributed. The reason for that is this extra carbon that methanol has over water. Carbon is more electronegative than these hydrogens that oxygen has, therefore can more evenly distribute the electron density in the entire molecule. But one thing to keep in mind is that these are still both polar molecules, but water is just more polar. Let's take hexane, for example. Hexane is composed completely of carbons and hydrogens. There's no electron withdrawing group or highly electronegative atom to kind of hog the electrons. Therefore, the electrons are more evenly distributed through this whole entire molecule, therefore making hexane not very polar at all. So another thing to consider is that polarity of a molecule is dependent on the whole structure of the molecule rather than just one particular functional group or atom. For example, ethyl acetate has 2 oxygen atoms, but it's less polar than methanol. Having these 2 electronegative atoms helps more evenly distribute the electron density versus having just 1 electronegative atom. So you can imagine that polarity can get kind of confusing for large complex molecules that have many electron withdrawing or electronegative atoms. Another thing that I want to point out is that polarity can be quantified numerically. There is a polarity index online, which I've shown on the bottom in table 1 with some values of some common organic solvents. The higher the value, the larger the polarity, and the lower the value, the lower the polarity. These values are determined through experimentation. However, so if you ever get confused on polarity, you can always just look up some of the values. But it is nice to be able to kind of reason your way through what is a polar molecule versus what is a nonpolar molecule. Next, let's get back to TLC and how it actually works. The first thing you're going to do is you're going to spot your analyte onto your TLC slide. If you have a solid, you're going to have to dissolve it in some sort of solvent. If you have a liquid, you're going to have to dilute it to make sure it's not too concentrated. After you prepared your analyte for spotting and you spotted the slide, you're going to prepare your TLC chamber with your mobile phase inside the TLC chamber, which is shown here. Then you place your TLC slide inside the TLC chamber and you cover it with a watch glass or whatever type of cover you have for your TLC chamber. The mobile phase is going to be allowed to work its way up the TLC slide, separating your analyte by its different components. And once again, they separate by polarity. Your finished TLC is going to look like what's shown on the right here. But one thing to keep in mind is that the amount of spots you will have will differ. In this particular example, it shows 3, but sometimes you'll have 1, you'll have 2, you'll have 5. It all just depends on what your analyte is. These analytes will move at different rates depending on the solubility in the mobile phase and its affinity for the silica. The more polar molecules have a high affinity for silica, which is a polar molecule, and will move slower than the nonpolar molecules that have less of an affinity for the silica and will therefore move at a faster rate. So you can imagine that if you wanted to move those polar molecules faster, you would have to use a more polar solvent. So something to keep in mind is that remember that like dissolves like. You might have heard that in Gen Chem. Nonpolar dissolves nonpolar, and polar dissolves polar. So once you remove your slide from the TLC chamber, you want to let it dry. After that, you'll probably be a bit confused because you probably won't see anything. Well, that's because some compounds are UV active and can only be seen under a UV lamp. Once you take your slide to the UV lamp in the back of the room, you will be able to see your mixture separating on the TLC slide, which will look a little bit like the image on the far left. You want to take a pencil and mark these spots because once you remove it from the UV light, you won't be able to see these spots. So keep in mind that some spots are UV active, some aren't. Sometimes spots can be seen with the naked eye, but in our case, that won't happen. But there are ways to visualize these spots that aren't visualizable using a UV lamp or your naked eye. One method that we are going to do is called iodine staining. The idea of iodine staining is that when you fill a chamber with iodine and place your developed TLC slide inside that chamber, the iodine vapors will adhere to the spots, making it visible. You will see these spots turn yellow like the picture on the far right, and you may even be able to see spots that you weren't able to see under the UV lamp. So now that we've visualized the spots, we can extract information from them. The amount that each component of a mixture travels up the TLC slide can be quantified using retention factors, or RF for short. The RF value of a spot can help us identify these unknown analytes. The RF value is the ratio of a spot traveled versus the length of the origin to the solvent front. For example, to determine the RF value of component A, you would take the length it traveled from the origin to the spot that you visualized, divided by the length of the origin to the solvent front, which gives us a ratio or retention factor. You can then use this retention factor to compare to a known standard to identify what component A is or most likely is. So that brings us to what we're actually doing today finally. In this experiment, we will be using TLC to determine the composition of some common over-the-counter analgesics. You will be given 4 known compounds: acetaminophen, aspirin, caffeine, and salicylamide, and you will take TLCs of all of them, and then you will record their RF values. You will then take TLCs of the analgesics, and then you will tell us exactly which of these compounds are contained in these analgesics. Using the data from the TLC, you should be able to identify these unknown samples based on these RF values that you've collected. So now I'm going to give you a summary of the procedure and some tips on how to make this lab go as smoothly as possible. So the first thing you're going to do when you start the lab is you're going to spot your reference plate. The reference plate is essentially your known standard, the known compounds that you're going to use to identify your unknown spots. A good rule of thumb is that the origin should be about 1 centimeter from the bottom. Additionally, you want about 1 to 2 millimeter spots when you spot the unknown or knowns. If you make the spots too big and blotchy, it won't separate very well. It'll just look like a big blob when you go to visualize it under the UV light. So what I like to do is I just like to give a quick dab, just touch it real quick to the slide. You might not get it the first time, it takes practice. Next, you're going to develop your reference plate in 0.5% glacial acetic acid and ethyl acetate. So in a normal laboratory, you would have to determine that solvent system yourself. But for convenience, we're just going to tell you. Something to think about maybe is how polar is this mixture, or even if this is a polar mixture, how polar is the compounds that we are going to be identifying today. After you develop your slide, make sure you mark your solvent front. That's very important, or else you won't be able to calculate your RF value. After you've let the slide dry, you're going to observe it under the UV lamp. Make sure you mark the spots after you're done observing it, because once you remove it from the UV lamp, it will disappear. Next, take the RF values. You're going to want to illustrate your TLC slide in your lab books with all the RF values. Next, you're going to spot your sample plate. And the sample plate will be developed the same way as the reference plate. Once again, you're going to observe it under UV lamp and then take the RF values just like the reference plate, and you're going to make some final conclusions about what is what using your two plates. So lastly, we are going to iodine stain both plates. So the reason iodine staining comes last is because it's non-reversible. Once you do the iodine stain, you're going to take it back, you're going to make any observations you need to make, write it all down in your book, and then you're going to tell us exactly what is what again. And that will conclude the lab.